Hi everyone. In this lesson, we're going to look at how to find extrema for functions of two or more variables. Now before we start, let's recall how we found relative extrema for functions of a single variable. So if you're given a function of a single variable, remember it might look something like this. Okay, so here we have a function of a single variable, and recall that wherever you have extrema, like here, here, and here, that's where your derivative is either going to equal 0 or does not exist. So remember what you did to find relative extrema for a function of a single variable. You would set your derivative equal to 0 or dne. You would find these values, and that would indicate where you may have possible relative extrema. Now, just because a point C solves this equation doesn't guarantee that you're going to have a relative extreme value at that point. For example, if you look right here, the way I drew this, right here, that's also going to satisfy f prime of x equaling 0, but you don't have a relative extrema at that point. It just goes up and then continues to go upward. So that's how you found relative extrema for functions of a single variable. Now recall also that once you found the values C that satisfied these equations here, then you either use the first derivative test or the second derivative test to determine whether you had a relative max or min at the critical points. Now, in this case, for functions of two or more variables, the first derivative test isn't really going to apply. We're not going to have something that's analogous to the first derivative test. For the second derivative test, just briefly remember how that worked. You would look at the second derivative of f at your critical points, like right here at that value, call that one C1. Now, if your second derivative, like at this point right here, your second derivative would be negative, that means your function is concave down at that point, so that means you would have a relative maximum. On the other hand, if your second derivative were positive, that would be like right here, then you would have a relative minimum because your function would be concave up at that point. And also remember that if the second derivative were equal to 0 at a critical number, then the test fails. You would have to go back to the first derivative test or use some other analysis to determine if you have a relative max, minimum, or neither. So that's a quick summary of how you found relative extrema for functions of a single variable. Now let's take a look at how we find relative extrema for functions of two or more variables. Now, once again, the first thing we're going to have to do is identify critical numbers. Now, the critical numbers for a function of two or more variables is going to be a little different, but pretty similar. We're going to be looking for where our first partials are equal to 0 or do not exist. So that's our definition that we have down here to start with. So here's our first definition for a critical point for a function of two or more variables. So we say that the point x0, y0 over a region R where f of x is defined is called a critical point if either one of these two conditions holds. Either the partial with respect to x and the partial with respect to y are both equal to 0 at that point. So then this would be a critical point, and that's where you may have a relative max or minimum. Remember, it only tells you you may have a relative extrema there. It doesn't guarantee existence of the relative extrema. So that's the first type of critical point where these two are satisfied, or either the partial with respect to x or the partial with respect to y at this point does not exist. So if one of these two conditions holds for this point, then we call that a critical point. And those are going to be where you may have possible relative extrema. Once again, it doesn't guarantee it, but it's where you may have it. Okay, now just some graphics down here illustrating why we need to consider these points down here. So the reason condition 1 is an important point where your first partials are both equal to 0, if you look at these two graphics right here, you see right here, you can see that your partial with respect to y and then your partial with respect to x going parallel to the x-axis. You know, they would both be 0 right there at that point, okay? Because once again, you know, if you took a slice through that point parallel to the zy plane, you know, it would look like the blue curve that we have there. And you see that's your partial with respect to y would be 0 there. Or if you took a slice through that surface parallel to the zx plane, then your function would look like this with respect to the xz axis, and you see you would have your partial with respect to x equaling 0 right there as well. So that's why we're interested in these points. Over here you have now this one, as I have illustrated, is a relative minimum. Over here, similar picture for a relative maximum, right? Your derivative with respect to y or with respect to x would both be 0 at that point. Okay? So that's why we're interested in those. On the other hand, like right down here is a picture illustrating why we are also interested where either the partial with respect to x or the partial with respect to y may not exist. Because right here you see you have a cusp at that point. So that's where your partial with respect to x and or your partial with respect to y may not exist. Now you only need an or statement here because you could have the partial with respect to x. You could have, like, if you cut a plane through your surface parallel to the zx axis, it could form a cusp at x0, y0, so it wouldn't be differentiable with respect to x. But if you cut a plane through it parallel to the zy axis, it might still be differentiable with respect to y at x0, y0. So you only need an or here. Now in this picture, both f of x and f of y would not exist because you have a cusp in any direction at that point. Okay? So in other words, wherever you have a cusp, that's where your partials, one or both of your partials, may not exist. And you can see you have a relative maximum at that point. Okay, now keep in mind down here we have a graphic showing why if the partials are both equal to 0, you may not have a relative maximum nor a relative minimum at a point where both partials are equal to 0. So, you know, that's showing you that even though you have a critical point satisfies either condition 1 or condition 2, doesn't guarantee that you have a relative maximum or minimum. For example, in this graphic right here, you see right there at 0, 0, you would have a critical point because the partial with respect to x is 0 and the partial with respect to y would be 0 at the origin. But you can see this is a saddle surface. You have neither a relative maximum nor a relative minimum at 0, 0 for this particular function, even though both partials are equal to 0 at the origin. So that indicates that just because you have a critical point doesn't guarantee you're going to have a relative maximum or minimum. All right, so let's take a look at a few examples before we continue. So let's just look at some examples where we find critical points first. So here's a simple function, f of xy equals 4xy minus x to the fourth minus y to the fourth. Let's locate the critical points. So we just have to find where the partials are both equal to 0 or they do not exist. Now, since this is a nice function up here, we only have powers of x and y. It's a polynomial in x and y. These partials are going to exist everywhere, so we don't need to worry about them not existing anywhere. So we take the partial with respect to x. Right there it is. Right? Derivative of this with respect to x, 4y minus 4x cubed. Derivative of this with respect to x is 0. So there you go. Derivative of this with respect to y. Derivative of this with respect to y is 4x. Derivative of that is 0. Derivative of y is 4y cubed. So there are the partials. And now we just need to set each of these equal to 0 and solve for x and y. So setting the first one equal to 0, that implies that y equals x cubed. Okay, so along this curve in the xy plane, that's where the partial with respect to x will equal 0. Setting this equal to 0, solving this equation right here, just taking the 4y cubed over, canceling the 4's, you get x equals y cubed. Okay, so x equals y cubed looks like this. It's going to go like that. Okay, let me put that in red. It's going to go like this. So we see that the points where both of these are equal to 0 are going to be right here, here, and here. Now this is -1, -1. That's 0, 0, and that is 1, 1. Now to find those algebraically, what you can do is this. So these are both of the equations. We have to find simultaneous solutions to both of these equations. So what we can do here is we'll take this equation right here, x equals y cubed, and we'll substitute in x cubed in for that y right there. You see that? So we get x equals x cubed cubed. So that's x to the 9th. Take this over to the other side. X minus x to the 9th equals 0. That's the same as x times 1 minus x to the 8th power is equal to 0. That implies x can either be 0, 1, or -1. Okay. Now then, substituting 0, 1 and negative 1 back into the other equation, which is this one. Right? We use this equation to solve for the what x could be. Now we take those values, put them back into the other equation, and we get that y can be 0 when x is 0. When x is 1, y has to be 1. And when x is negative 1, y has to be negative 1 as well. And so you get these points. And we see that's exactly what we found up here graphically. All right. Now also keep in mind, I didn't mention one other thing here. This red curve right there, just jumping back here a little bit, x equals y cubed. You could also graph that as y equals the cube root of x, right? So that's how you get that red curve right there, y equals the cube root of x. All right, so now if we actually graph this surface right here, you'll see how these points do match up with locations where we have relative extrema. Now down here is a graph of the surface. So here's what that function, let's see, that was our function z equals, this is the graph here, z equals 4xy minus x to the fourth minus y to the fourth. Okay, and you see right there is the 0, 0. That's the one critical point. And if you plug 0, 0 in for x and y, you get z is 0. So now you see that's actually a saddle point. We have neither a relative maximum nor a minimum at that point. Right here is 1, 1 that we found. And if you plug 1, 1 in for x and y, you get back 2 for z. And you see that's actually a relative maximum for the function at 1, 1. We can see that graphically. Now, analytically, how do we do that? Well, we'll see in a second. We do have a test for that. Over here is negative 1, negative 1. If we plug negative 1 in for x, negative 1 in for y, you will also get back 2 for z. So there's that point, and we see that negative 1, negative 1 is also where f has a relative maximum. All right, so you see by identifying the critical points, we can identify where our function is going to have relative extrema, although we might also catch some saddle points as well. Now let's take a look at a test for determining whether we have a relative max, a relative minimum, a relative maximum, or a relative minimum at one of those critical points. Now recall, here is the second derivative test for a function of a single variable. So recall that once you identify a critical number c, if your second derivative is greater than 0 at that point, meaning your function is concave up, then you have a relative minimum at c. If your second derivative is negative, that means that your function is concave down. I'll put it right here, so concave down, so you have a relative maximum. Here it was concave up, relative minimum. If your second derivative is 0, then the test fails. Your function may be concave up, it may be concave down, it could even be a saddle point, so the test is inconclusive. You have to go back to the first derivative test to determine what type of relative extrema you have at x equaling c. Now, how does this test look for functions of two variables? Well, here's what it looks like. For a function of two variables, we call this our second partials test. So if f of x has continuous partial derivatives over an open region containing a point a, b, in which the partial with respect to x at a, b and the partial with respect to y at a, b is 0, and we let d be this quantity. So it's the second partial with respect to x times the second partial with respect to y minus the mixed partials squared. Then, if we take our critical point AB and plug it in here, if d of AB is positive and the second partial with respect to x at AB is positive, then you have a relative minimum at that point. So, as you can see, this test is a little more complicated than the second derivative test. On the other hand, if d of AB is greater than 0 and the second derivative with respect to x at AB is negative, then you have a relative maximum. If d of AB is negative, then f of x has a saddle point at AB. And finally, if d of AB is equal to 0, then just like with the second derivative test, the test is inconclusive at that case. You may have a maximum, minimum, or neither at the point AB. All right, so that's our second partial test. And it is more complicated than the second derivative test, but that's to be expected because we're dealing with functions of two or more variables here. Well, this test is only for a function of two independent variables. So let's take a look at this in action. Now in this example, we want to consider the previous example where we had worked with this function, recall that, and we want to apply the second partials test to identify the relative extrema. Remember that visually we saw that 0, 0 was a saddle point and 1, 1 and negative 1, negative 1 were relative maxima. So let's apply the second partials test and see that it tells us that this will be a saddle point and these two will be relative maxima. So remember, we need to calculate the d, which is given by this up here. And in this part of our notes, just note that this can also be evaluated as the determinant of this matrix of second partials, right? If you multiply down, add, and multiply up and subtract, you get this. So that's just an interesting thing to take note of, that d in the second partials test can be evaluated as the determinant of that matrix. Okay, so we need to evaluate these quantities. So recall that fx for this function is given by 4y minus 4x cubed, differentiating this with respect to x. F sub y is this, differentiating this with respect to y. And so then differentiating these with respect to x and y themselves, we get fx. X is going to be negative 12x squared. That comes from here. Fyy is going to be negative 12y squared. That comes from differentiating this with respect to y. And then fxy, if we differentiate this with respect to y, we just get back 4, right? Or you could differentiate this with respect to x, because remember, fxy equals fyx. So now we can evaluate d, and let's see what we get. So now remember, d is this quantity right here. And so just multiplying these together and subtracting the square of 4, we get this for our value of d. Now we can evaluate then d at each of these points. So first of all, note that at 0, 0, evaluating d of 0, 0, 0 in for x, 0 in for y, we get negative 16, right? Because this will go to 0. That's less than 0. So if you look back at the second partials test in your notes, you'll see that the test tells us then that 0, 0 is where f of x has a saddle point. If you plug 1, 1 in for x and y in for d, you get 128, which is positive. Okay, so that's positive, but then we need to check out fxx, the second partial with respect to x, to see if it's either positive or negative. So if we plug 1, 1 into this right here, we get back negative 12, which is negative. So if you look back in your notes, because the d is positive and fxx is negative, that tells us that 1, 1 is where f of x has a relative maximum. Then we do the same thing with negative 1, negative 1, that critical point. d of negative 1, negative 1 is also 128, which is positive. Now, since this is positive, we now need to check out the second partial with respect to x of f at negative 1, negative 1. So plugging these values in here, we also get back negative 12, which is negative. And so the second partials test tells us that negative 1, negative 1 is where f of x has a relative maximum. Okay, and so there you go. That's how we apply the second partials test. You just have to determine which of these cases right here you fall into, which of those cases. So we saw that for this example, which was also the previous example, that we fell into these two cases. This held and this held, so we had a relative maximum. And we also had the case where we had a saddle point. And recall that looking back at the graph of that function, once again, this was the graph of that function, the surface. And you see that at 0, 0, we do have a saddle point. 1, 1, and negative 1, negative 1, you do have relative maximum. Okay, so that's using the second partials test to verify what we had seen graphically previously. Let's take a look at another example. So let's consider this function. Let's identify the critical points and then use the second partials test to see if we can determine which ones are relative maximum, minimum, or saddle points. Or the test might fail. We'll see. So to identify the critical points, remember we take the derivative with respect to x and the derivative with respect to y and find out where these are 0 or do not exist. Now, we don't have to worry about do not exist, not existing in this case because this is a nice polynomial. But, you know, technically you would also need to find where fx, dne, or fy, dne as well. But we don't have to do that in this case because it's such a nice function. So anyway, taking the derivative with respect to x of this, we get negative 3x squared plus 4y, right? That's the derivative of this with respect to x, right? Right here, negative 3x squared, derivative of this would be 4y, and derivative of this part would be 0. Derivative with respect to y is going to be this, right? 0, 4x minus 4y, and then derivative of 1 is 0. Okay, so we have to find simultaneous solutions to both of these equations. So all we have to do is, I've got y's on both sides, so it's nice and convenient just to take this and substitute it for that y right there, and then just solve an equation involving x. So that's what we have right here. Where does 3/4 x squared equal x? Well, that's just a nice quadratic we can solve like this. Just take the x over, factor out an x, and this tells us that x can either be 0 or 4/3. Right? So there you go. Substitute 0 and 4/3 back into either equation here, and this is the most convenient one. And so we then have these as our critical points. If x is 0, y is 0, and if x is 4/3, y is 4/3 as well. So there are the critical points. Okay, now we can apply the second partials test. Doing that down here, we need to evaluate d, right? That quantity right there. So we need to take our second partials. So fxx, let's just move back up here. Recall that fxx right here. Okay, recall that this is derivative with respect to x. Taking the derivative again with respect to x, we get negative 6x. So there you go. Differentiating this with respect to y, you get negative 4. And differentiating this with respect to y, you get 4. Or differentiating this with respect to x, you also get 4. And so therefore the quantity d, multiplying these two together and subtracting the square of this, you're going to get 24x minus 16. Now we need to evaluate d at these 2 points. So first of all, d at 0, 0 is negative 16. Okay, that is less than 0, so we know right away that we have a saddle point at 0, 0. Then putting in 4/3 in here for x and y, right here for x and y. Well, we only have an x. We get this, which is 16, which is positive. Okay, well, okay, now we need to check out the second derivative of f with respect to x at that point. Well, if, let's see, that's right here. So if you plug in 4/3 in for this x, you get a negative number back, right? You get this, which is negative. And so therefore we see that these two things, looking back at the second partial test, tell us that at 4/3 we have a relative maximum, and that's pictured right over here. And right here is 0, 0, that is your saddle point. Okay, and there you go. That takes care of that example. Now let's take a look at this example. This is a quick example that shows why the test fails when d is equal to 0. So if you look at these two functions here, this one and this one, obviously g is just negative f. Okay? Well, obviously this function, if you look at it, down here we have the graph. I'll scroll down in a second. This function has a relative minimum, actually an absolute minimum at 0, 0. And this function has a relative maximum, actually an absolute maximum at 0, 0. However, doing some quick calculations, we'll see that d for both of these is 0. So you see we have two functions, one that has a relative minimum, one that has a relative maximum, yet d is equal to 0 for both of them. So that's why the test fails, because we have an example here where d is equal to 0, but we have different relative extrema. So that's why the test fails. And just verifying that d is equal to 0 for both of these. For example, with f, just evaluating this right here, partial f with respect to x is going to be this. Partial f with respect to y is this. Now these are both 0 at 0, 0, so that is a critical point for this function. And then evaluating d at that point, okay, we need to calculate our second partials here. So fxx, differentiating this, that's 12x squared. Fyy is also 12y squared. And then fxy is going to be 0, differentiating this with respect to y. We end up with this. So now you see d for the function f at 0, 0 is just 0. And since g is the negative of f, you can easily see that d is also going to be 0 for g. Right? So the d, let's call this the d sub f, that's the d for the f function. And then you can verify that d sub g at 0, 0 is also 0. You can easily verify that, since it's just the negative of f. And so now you see that's why the test fails when d is equal to 0. And down here we have the graph for these two functions. Right here's the graph of f. You see you have a relative and an absolute minimum right there. And here's g. You have a relative and actually absolute maximum at 0, 0 as well. Okay, let's take a look at this. Now in this next example, we're going to see how we can identify absolute extrema for a function of two variables over a bounded region in the Cartesian plane. Previously, we only identified relative extrema using the second partials test. So with this example, we're going to consider this function. So this is just a paraboloid with vertex located at 1, 1, 0. Notice if we put 1 in for x and 1 in for y, we get back 0 for f. And that's going to be where the vertex is. The vertex in the xy plane is at 1, 1. And it has a value of 0, function value of 0. And we want to identify the absolute extrema for this function over this region in the xy plane. So the region where x is greater than or equal to 0, y is greater than or equal to 0, so we're in the first quadrant, and y has to be less than or equal to negative x plus 3. Now, what this region looks like is down here. So here's what our region R looks like. It's just this triangular region in the xy plane. Notice that this is one bounding curve, x equals 0, y equals 0, and this is the line y equals negative x plus 3. So remember, y is supposed to be less than or equal to negative x plus 3. So all the points satisfying that are going to be below this line. And then they must be to the right of this line and above this line, above the x-axis and to the right of the y-axis. Okay, so that's our region R. Now, in this next graphic, we have the surface overlaid over top of this region. Right here is what it looks like. So here's the surface. That's the paraboloid. Notice we have a vertex right about there. That's at 1, 1 in the xy plane. And what we have to do is find where f has a maximum and where it has a minimum over this region. So if you think of projecting this triangular region onto the surface, you know, it might look something like this. You know, maybe it would look something like that. And then we want to find the maximum and the minimum values of f for this region R projected onto the paraboloid. So what we have to do is we need to create a list of points in R where f may have relative extrema. So we're going to identify the critical points for f, in particular those that are interior to R. As we'll see, 1, 1 is going to be a critical point. And then what we want to do is we want to restrict f to just these curves and identify critical points using techniques from Calculus 1. And then we're going to create a list of points, evaluate f at each of those points, and pick out the biggest and smallest value for f. Okay, so let's do that. So the first thing we want to do is to determine if f has any relative extrema over the interior of the region R. So we find our critical points. So we set f of x, that's going to be 2x minus 2, equal to 0, right? Remember, just remember here that f is the function x minus 1 squared plus y minus 1 squared. So differentiating with respect to x, we get this. Differentiating with respect to y, we get this. Set it equal to 0. Once again, we don't need to worry about where f of x or f sub y dne, because this is a nice function. Now, setting each of these equal to 0, of course, this tells us that x equals 1, and over here y equals 1. So there you go. 1, 1 is a critical point, and that is inside the region R. Notice that it does satisfy all three conditions for the region R. Remember, x had to be bigger than or equal to 0, y had to be bigger than or equal to 0, and y had to be less than or equal to negative x plus 3. And this point does satisfy each of these three conditions. So it is in the interior of R. Now what we need to do is identify critical points along the boundaries. Okay, so what we do now is, first of all, let's consider critical points along the curve y equals negative x plus 3 for x between 0 and 3. Remember, for our region R, it looked like this. The curve y equals negative x plus 3, that crosses the x-axis at 3, and it crosses the y-axis up here at 3 as well. Okay, and so for this curve, x is being restricted between 0 and 3. Okay, notice that. All right, so what we do now is we substitute this into y in our function. You notice this was the y previously, so we substitute that in for y. So there we go. So now we have f is just a function of x. So we're only considering along this curve right here. And simplifying this, you know, of course, this part right here simplifies as negative x plus 2 squared. And then foiling this out, you're going to get 2x squared minus 6x plus 5. Just FOIL that out, combine like terms, that's what you get. Now we need to identify possible extrema for this function. over this interval. So now this is like a calculus 1 problem now. So what do? We differentiate this, find where it's equal to 0 or does not exist, take the endpoints of the interval, and test all of those points, see where f is biggest and smallest. Okay? So, taking the derivative of this with respect to x, we get this. We set it equal to 0 or dne, technically or dne, but we don't need to worry about dne in this case. And this tells us that x is going to be 3/2. And we must also include the endpoints. Remember, in calculus 1, when you're finding the maximum or minimum over an interval like 0 to 3, you have to throw the endpoints into your list along with the points where your derivative is 0 or does not exist. So therefore, we have this list of points now that we must test. So these are points where f might have relative extrema over this line. And now if we substitute these values back in for y, back into this equation, we get the list of points 0, 3, 3/2, 3/2, and 3, 0. So you notice those are these points right here, this one, and right about there in the middle. Okay, so we need to test f at those 3 points along with this one as well. That's in the interior, so we're going to have to test that point too. Now we need to do the same thing that we did for this curve along these 2 curves. Okay, so let's do that. So now along the curve y equals 0, remember that is going to be from here out to 3. Okay, and so of course x is between 0 and 3. What we do is we substitute 0 in for y into our function. Right there it is. And we get this function. Now we need to take the derivative of this, set it equal to 0 or dne, and identify those x values. So right here's the derivative. We set it equal to 0. We get x equals 1. Okay, so that point is like right here, right about there. And we also need to include the endpoints. Now we already had this one endpoint from the previous problem. Okay, so this one is just repeated from the previous part. And then we get this list of values for x, 0, 1, 3. And then substituting those back into y equals 0. Okay, that's the curve we have to substitute them back into. So if x is 0, y is 0. If x is 1, y is 0. If x is 3, y is 0. Well, in other words, all these points have y coordinate of 0. Okay, so now we need to also test these points. Okay, so now we have the list of points. Remember, thinking back to what we did previously, we started out with 1, 1, and then we had the points 3, 0, 3/2, 3/2, 0, 3, and now we have these points to add to this list. We already have 3, 0, but we need to add these points as well, 0, 0, and 1, 0. Okay, so these are all the points that we're going to have to test our function at to pick out the biggest and smallest value. Now we need to do the same thing along this curve where x is equal to 0, along this boundary. And that's what we're doing right down here. So let's do that. Okay, so now along the curve x equals 0, with y between 0 and 3, remember we only want to go up to 3 on the y-axis. If we put 0 into our function right there, we get a function only involving y, and the y is supposed to be between 0 and 3. So now this is a Calc 1. This is another problem from Calc 1 where we have to find the minimum and maximum of this over this closed interval. So we take the derivative, right here it is. We set it equal to 0 or dne, and setting this equal to 0, we get y is 1. And then we also need to throw in the endpoints, 0 and 3, coming from here and here. And we get this list of y values. Substitute each of these back into our bounding equation. Well, x is always 0, and we get this list of points, 0, 0, 0, 1, 0, 3. So we need to add these to our list over here. Now we already have 0, 0, and 0, 3, so we just have to add 0, 1 to it. And there you go. We now have our list of points that we have to test f of x over to pick out the biggest and smallest values. And that's it. So just to summarize here with this graphic down here, here's our list of values that we found. So once again here, this one we found first by just setting fx equal to 0 and fy equal to 0. And then we also found these boundary points. And these boundary points were found by taking the equation like y equals negative x plus 3, substituting this in for y into our function, and then we get a function of only a single variable x, which over the interval here, x was supposed to go from 0 to 3. And then we found all of the critical points for this function, just a function of a single variable, over this closed interval. And that gave us back 0, 3/2, and 3. And then we plugged 0, 3/2, and 3 back into here to find the y coordinates. Okay, now all we have to do is test f at each of these points, pick out the biggest and smallest values. And that's what we're doing down here. So here's the function value at each of those points. Obviously, the smallest value is 0 at 1, 1. And the largest value is 4. So here's our max. And we also have another max right here. And this one was our minimum. And so we have two maxima occurring at 0, 3, and 3, 0. And so there you go. We have now found the absolute minimum to be 0 for our function occurring at 1, 1. And we found that the absolute maximum is 4, and that occurs at two different locations in the xy plane. And we can see this graphically if we look at these up here. So it makes sense that we have an absolute minimum of 0 at 1, 1 because that's where the vertex is. And then it also makes sense that this point and this point would be where we have maximum values for f, because it looks like they're furthest away from the vertex. They're actually a little further away from the vertex than the origin is back here. And so when we project them up onto the surface, that's going to give us our largest function values. And it just so happens that when we project them onto the surface, we get the same value of 4. And it sort of looks like we're going to get the same value right here. If we move that over and move this over like that, yeah, sort of looks like we should be getting the same value of 4 right there on the z-axis. And so there you go. So that's how you can find an absolute extrema for a function of two independent variables over a bounded region in the xy plane.